I have struggled my whole life to try to understand consciousness. It's been an obsession. You have given me a new way to think about it. Rather than starting with the brain, which I've always assumed, which I did in my early career, you've asked me to start with the mind, to understand what the mind is, and then to create a theory, to integrated information theory, unique approach, to look at the world, brains or whatever, that can create, that are mechanisms that can create and generate the kinds of characteristics of mind which you start with. Okay, integrated information theory. If it is a theory, it has to be able to explain things that are not things that cause the theory that you use to generate it, and predict. So what can you explain and what can you predict?
Perfectly put, yes. Otherwise it would not be a scientific theory. I grant you that. So integrated information theory says, in essence, that you need a very special kind of mechanism organized in a special kind of way to generate experience consciousness. Does that fit with what we know about the brain and consciousness, which is where we know the most? And does that explain some of the paradoxes that we have encountered when looking at the brain and consciousness? So one, which is perhaps the easiest to understand, is the contrast between the cerebral cortex and the cerebellum in our own brain. That's our brain, so we know a little bit about that. The cortex has around 22 billion neurons.
The cerebellum, that's the surface of the hemispheres.
Yeah. And the cerebellum is smaller. It's in the back here, but it has more than 60 billion neurons probably, something like that, so more than the cortex. And yet it is a fact that if you take the cerebellum out of the brain, which is rarely but occasionally done for medical purposes, or in some rare cases if you're born without a cerebellum, well, you throw it in the surgical wastebasket, so it's gone. This is more than half of the neurons in your brain. Your consciousness doesn't change.
Doesn't change.
Does not change at all, essentially. Yes, there are some things that you don't do as well as before. Of course, you walk differently and so on, but it doesn't change. And if you take away the cerebral cortex, less neurons, you are completely gone. And there's plenty of evidence for that. So what is wrong about the cerebellum and what is right about at least some part of the cerebral cortex? That one doesn't seem to do anything to consciousness, the other one instead is necessary for consciousness. It's not that the cerebellum is made of, second-class neurons. They're not only more numerous, but they have all the right genes and all the right receptors, and it has tons of connection. It has maps of the world in all the sensory modalities, and it controls the output, and it's even heavily connected to cortex. Mm-hmm. So if you just look at it, this is a beautiful paradox. This doesn't do it, this does. They're both neural, they're both fantastically complicated, they do all kind of neural things together. This is really one of those things that should make you think, and you have to have a theory that explains that. Integrated information theory explains that, at least in principle, because it accurately goes back to what we know about the cerebellum. It shows that that's arranged in a way that's primarily modular. Even it is very complicated. Every little piece of cerebellum does its own thing, takes input, processes them, produces output, in a way that's substantially independent of all the others. This is exactly the way you should not be organized if you want to form a maximally irreducible conceptual structure when you actually see what it does. The cortex, we've known for a long time, is different. It is made of lots of local things that do their specialized things. Some deal with colors and some with shapes, some with motion, some with sound and so on. Every piece of cortex does a different thing. But they also interact in this most intricate way because they are connected in all kinds of manners. So it has sort of the right structure for generating consciousness. That theory clearly explains that that is the right structure and the other one is not. I'll give you another example, and that is sleep and wake, which is one reason why I've tried to study sleep to understand consciousness. So I say that when you lose consciousness, well, the best example we have of that is when you fall into dreamless sleep. Early in the night, typically, you're gone. If I wake you up and ask you what was going through your mind, nothing at all. So that's the only case in which we really know what it means not to be there. It means nothing at all. Interestingly enough, we have known for a while that the cerebral cortex itself now remains active, even in this deep sleep. Maybe a little bit less, in a slightly different way, but it's still active. So the cortex is there, it's the same anatomy. The neurons are firing or not firing, just like when you're awake, and consciousness goes away. How can that be? This is another of these paradoxes. And once again, integrated information theory now provides a consistent explanation for that. It says that when you are asleep, even if it is the same organ, the cerebral cortex, and even if it is firing, just like in wake, well, something about it must be such that the information integration is not happening. So they are still active, the neurons are the same, but there is no integrated information. It does not generate a maximally irreducible conceptual structure. Now that's an explanation that the theory has, but it's also a prediction. So if that is true, we should be able to measure integrated information in some way and see, does it actually go down when you go from wake to deep sleep, even if your brain is still firing happily along. So together with some colleagues of mine, primarily with Marcello Massimini, who is now a professor in Milan, we, when we were in Madison, Wisconsin, we tried to develop a way to roughly evaluate integrated information. Now, we can't really do integrated information as you would do for a very simple system where we can calculate everything. We can get an idea. So we use transcranial magnetic stimulation, which is a way with a paddle that you put on your head to induce a current in a particular part of your cerebral cortex. So like an electrician, you're going in and buzzing it, okay, zapping it, that's the sort of term we use. And then we use EEG, many electrodes of electroencephalography, to record the response of the cortex to that zapping. And we reason that if you're conscious, there should be some sign that the cortex is capable of integrating information. If you become unconscious or minimally conscious, as in deep sleep, that information integration should break down. That's precisely what we saw. If you inject this current and you're awake and conscious in your brain in this spot at a particular intensity, we see the cortex respond in all kinds of complicated ways for roughly a third of a second. So activation goes here, there, there. It's like a very beautiful network of roads where traffic is going on and things are interacting beautifully. Your same brain, the same person, of course, same spot, same intensity of stimulation. Now you're in deep sleep in the phase in which you are not conscious. Well, then, even if the brain is active, it responds to the stimulation, but it responds only locally. The electrician is only able to zap that piece, and somehow it doesn't go anywhere else. The system breaks down. It's not one entity, but it breaks down into many little entities, a little bit like the cerebellum. It becomes modular, even if the connections are still there, and the neurons are still there, and they are still firing. We are still trying to understand exactly how that is that information integration breaks down, but as predicted by the theory, it actually does break down when consciousness goes away.
Well, one thing we know when we're asleep is that the waves in the brain go from very high frequency, small, to slow frequency, larger activities, which are a synchronous approach in the brain during sleep. And is there any implications that would have?
Yes. In fact, if you model this and you study this in detail, what happens there is even if the neurons are synchronous, they lose the ability to talk to each other. Because whenever they fire strongly, then they immediately have to go into what is called the down state, the stop firing. So they can't really conduct a conversation because it's as if every time I begin to talk to you, suddenly it goes blank. Then you talk back, but it goes blank. And so suddenly there is no conversation anymore, even if we are both talking, okay? And so something like that is what happens in sleep. The theory predicts that this should happen also in other states of unconsciousness. The best one we can study are anesthesia. So in various studies done in collaboration with a group in Liège, Stephen Laurie and Melanie Bolly and others, we have looked at the integrated information, how it changes when you're anesthetized with this anesthetic, that anesthetic, and other anesthetic. And they all have different mechanisms of action. Nevertheless, they all make you lose consciousness. So the prediction is you should see with TMS-EG again that there is this breakdown of information integration. And in short, that's what happens every time. When you lose consciousness, integrated information breaks down. When you regain it, it comes back. In fact, when you dream during sleep, integrated information also comes back, as we showed not long ago.
And during dreams, do you do TMS?
We do TMS. It's very difficult to do that because you don't want to wake up the person, etc. But when you lose consciousness in sleep, in deep sleep, it breaks down. But a few minutes later, maybe, if you do the same thing, suddenly you see the brain responding as one entity again. The cortex becomes integrated. And if I wake you up then, you're going to be conscious, as predicted by the theory. Another important thing is studying patients with brain damage. So there we tried again to see, in people who are clinically vegetative, so most neurologists would think they are not conscious indeed, okay? Is it true that if we do the same TMS EG approach, we are going to find that information integration breaks down in each and every one of them? And the answer is, now we have studied many of those, that is always the case. So when somebody is definitely unconscious, as judged by neurologists, integrated information is very low.
And what you mean by that is when you do your TMS magnetic stimulation one place, you're recording from all over the brain.
And in complicated manners. So there's both information and integration.
Right.
And instead, if a person is vegetative, the response will be local, so it's not integrated anymore. That's typically what happens. Or it is global but homogeneous, so you lose the information. So either you lose the information or the integration or both. In patients who have what is called a minimally conscious state, which is we suspect they are conscious, we can say track you with their eyes, etc. Well, there, while the brain is damaged, integrated information is actually high. It may not be as high as in you and me, but it's definitely much higher than when it is vegetative. So this actually may be used now. We're trying to use this as a way to probe consciousness in people who cannot communicate. Based on a theory that says what consciousness is, we can go in like an electrician, buzz the brain, see how it responds, and if integrated information is high, measured in a certain way, which is approximate but useful, we can suspect that indeed that person is there is somebody home or not.